So today, we have Dan Moran presenting. Dan is a senior graphics engineer at NCSoft, working on AAA mobile games developed in Unity. Dan's career in game development started as a programmer and artist on the Games for Health project Library with Equus Labs at Queen's University. He then spent a year as an independent developer, during which time he started the Making Stuff Look Good YouTube channel. MSLG teaches introductory to advanced level shader programming and explores how visual effects in popular games can be recreated in Unity. Dan is in many ways the go-to person for learning Unity shaders on YouTube, and has created really just a wealth of free content available to people, and it's certainly something you'll see on your assignment. So we're really excited to have him in the flesh here today. Please join me in welcoming Dan Moran.
All right, thank you very much, Matthew. This is week 6, which I believe the title topic for is technical art. And so who am I? Well, Matthew kind of covered it, but yeah, I studied at Queen's, did a thing there. Senior graphics engineer, NCSoft, Iron Tiger, that's in San Mateo. I'm a YouTuber. I put that in quotes because I think that's a really gross word, but you know. I run the channel Making Stuff Look Good, Introduction to Shader Programming, yada yada. You already covered all this. Thanks you, Matthew. I'm also a frequent game jammer who, those of you who are getting into game design, I really recommend that you start trying your hand at game jams, which are very rapid iteration, sometimes 48 hours, sometimes a 1 week, where you make a game. And here's just a plethora of games I've made as part of game jams. So shaders, that's what we're here to talk about today. What are shaders? They are small programs written in a C-like language. We've got a couple different flavors of the language. We've got CG or HLSL, basically synonymous for one another, and GLLSL. You can think of the difference between the two of those as Windows versus Mac. It's a little bit more muddy than that, but and shaders define how each object in your scene, in your game scene, should be rendered. They're capable of running millions of times per frame, and it is millions. So if you think about every pixel in the screen needs to be drawn, and you've got 1920 by 1080 on your average display. That's 2 million pixels right there, times 60 times per frame, so that, or 60 times per second rather. So 120 million times per frame, or per second rather, these need to run. So that's a lot. But the best part about shaders is that they are a blend of engineering and artistry. So if you're kind of leaning a little bit towards the art side, but you're also really engaging with your technical skills, shaders are an excellent facet to explore. So let's look at some shaders in action. Hearthstone, a card game by Blizzard, brings their golden cards to life using shaders to do sort of procedural animations and effects on cards. Drive Club 3, I believe this is, somewhat famous for its incredible weather effects. It's rain simulation, all done on the GPU, all done shaders to represent those individual water droplets. And shaders can even completely change the look of a game. So you see here we've got a vanilla Minecraft down here versus one with some very creative use of post-processing shaders to really clean it up and make it look like something much more beautiful. So let's go on a whirlwind tour of a rendering pipeline. This is a game. Looks just like a real game, right? This is absolutely just dummy code. Shouldn't look like any real game logic at all, but it lets us get the point across. So every frame you can see you're updating, you're taking player inputs, you're moving the player position or whatever. And then after that, you need to show that to the player. So you need to draw that to the screen. You need to render. So we're going to be focusing on what happens inside this render function. So example of render function, we might do something like this. We might say, okay, for every renderer in our scene, we want to draw that renderer. And what do we mean by draw that renderer? Well, we want to be sending commands to our graphics card. We want to be saying, okay, graphics card, set the shader, set the technique with which we wish to draw this object. Then we'll say, set these extra material values. Those might be things like textures or colors or transformations, all kinds of things we might be setting on our GPU. And finally, we want to draw. We've got to draw the thing. So let's break into that last point there, drawing the renderer. And what does it mean to draw a mesh? What does it mean to have a mesh on our graphics card? Well, a mesh is uploaded as several lists. You've got a list of all the vertices. These are individual 3D positions relative to the space of that object. And then you've got a list of all the triangles, which is just indices into that previous list. So if you've got triangle 0, 1, 2, those are indices 0, 1, 2 of that first list. And every 3 elements of your triangle list represents one triangle. Sometimes it's called triangle soup because they don't have to coherently be in any order. So yep, if you ever hear the term triangle soup, it's not just mumbo jumbo. And then there's other stuff. There's all kinds of other things we might upload with our mesh. Texture coordinates, obviously very common if you want to sample any textures. Normals and tangents if you want to do any lighting calculations. Colors if you want to give things color. So let's do a breakdown of what the GPU is doing and which parts of that we have control over. So this is the first thing we have control over right at the beginning of the pipeline is the Vertex Shader. This is how we're telling the graphics card to take our positions from the local space of the mesh and translate them into 1920 to 1080 pixel coordinates on the screen. So our Vertex Shader takes that data, that mesh data, that position, and returns a 2D position essentially on the screen by doing something to it, by doing some sort of transformation. Then we've got the step we have no control over called triangle assembly, where we need to actually take all those vertices and turn those into actual mathematic triangles on the screen. We also do some other things like where the triangle goes offside the screen, we can say, okay, clip that, don't generate any data for that because it's not in front of the screen. Then we've got another step we have no control over called the rasterizer. That's where we're taking our, if you've ever seen the difference between scalable vector graphics and raster graphics. Scalable vector graphics are infinitely scalable. We can zoom in on the edges of them forever and never have any decrease in quality. Raster graphics actually represent pixels. So we need to take our triangles, which are mathematical representations, and actually transform those into pixels on the screen. And I'm sorry this part is super dry. I swear it gets more interesting in a little while. Then we get the fragment shader. This is the quote-unquote fun part. This is where we actually get to shade each fragment. This would do our lighting calculations, colors, texture samples. A lot of fun stuff can happen here. So this is the second part that we have a lot of control over here. And in here we return a color for the actual individual pixel at that point on the screen. And finally, we've got blending. You can see it's blue there. I've got it as blue because it's got some control. We don't have no control over it like these gray steps, but we don't have full programmatic control like we do the orange steps. We can basically do things like say, okay, if the pixel below us was this color and our pixel is the pixel we're returning is this color, just add those two together, and that's about the granularity of control you have. So Vertex shaders, they take mesh data as input and they return a position on the screen. And they transform that data using something called matrix multiplication. Those of you who have already taken linear algebra or plan on taking linear algebra, it's something you'll get a lot of familiarity with there. And they pass through other useful data to the fragment shader, like all that other stuff, normals, textures, all that. And the important thing here is that Vertex shaders execute once for every vertex in the mesh. So if you got your cube made up of 8 vertices for each 8 corners, your Vertex shader runs 8 times. So here's a example of the borderline most simple you can get with a Vertex shader, just about. And what this does is we take, let me put on the pointer here. Oh yeah, here we go. So here what we're doing is we're taking a vertex in a position and we're returning a position as well. So something that might be new to some of you here is an attribute called float4. Just like if you're familiar with floats in your C# code or what have you, except that there's 4 of them, so it represents 4 floats, a 4-dimensional vector. We've also got these things called semantics. These are forced on us by Microsoft. Thank you, Microsoft. These basically just say, more specifically, what does this float4 represent? So this position means literally position on the mesh. And SV position, this means position on the screen, more or less. Then we've got mul here. That's basically just the mathematic symbol for like do a matrix multiplication with this thing and this thing. And then we've got this big all capitals matrix MVP, this big scary thing, which is a value we pass into the shader, which tells it how to transform our position that we take in to our SV position, the position we return out. And we're going to break that down a little bit more, but I don't want to get too into it because it is pretty down in the weeds, and luckily you won't have to do too much of it. But the MVP matrix is model view projection. So it represents 3 matrices that are all multiplied together. The model matrix is the first step. It says how our vertices need to be transformed from a local coordinate system into a world coordinate system. So for those of you who have used Unity, you're familiar with the transform component that's on every single object. It has a translation, a rotation, and a scale. Well, this is how we basically pack that translation, rotation to scale into a matrix, which we can use to define how we move the vertices of its mesh. Then we've got the view. We've also got a camera in our scene, and our camera itself has a position and a rotation. So we need to make another matrix that says, okay, how does this affect our set of points, our points that are local to the mesh? Because if our camera is facing away, we don't even want to render this object, so we need to factor in the camera. And finally, we've got projection, which is kind of the weird one, a little bit harder to explain, so I won't do too many hand symbols. I've got a better slide for this in a moment. Basically, our camera defines clipping planes, a near and a far clipping plane, and a field of view, which kind of define this box. Let's skip ahead to the box. So you've got this sort of, your camera at the front here, you can see the near plane here, far plane at the back, and some object in the center, whatever. It's just a red cube here. And so if you can imagine what the projection matrix is doing is it's going to take this camera frustum and it's going to stretch out the front plane such that the whole thing's a cube. And if we did that stretch, if we did that distortion, what would happen to all the objects inside the view of the frustum? They might do something like this. So the purpose of this matrix multiplication is to make the vertices and meshes and objects that are closer to the camera look like they're larger, and the ones that are further away from the camera look like they're further away. So yes, you multiply all these matrices together and you get one big MVP matrix. Oh my God, thank you Unity to the rescue, because you never have to think about this or do this ever again. So brain dump, everything I just said, forget it, not important. The math is done for us by Unity. Shaders will always have access to Unity_matrix_MVP, do these transformations, and then even make it one step easier. They just give you a function. They just say, give me your position, I'll give you the SV position. That way you can't mess it up. So just let Unity hold your hand here. And yeah. So let's wrap on Vertex Shader so we get to the really fun stuff here. They're very boilerplatey. It's kind of the same code is going to be in every single Vertex Shader. You know, you're just going to be doing this one multiplication. You're going to be passing through your texture coordinates. There's a little bit of room for some creativity. Maybe you're moving those vertices using some fancy math or something. You're extruding along the normals. But usually you're just going to pass through your stuff and do all the really interesting stuff in the fragment shaders. So, fragment shaders, the fun part. Who's having fun? One guy, yes, sweet. All right, so these are the shaders which take data from our vertex shader, so anything that was passed through, and they return a color, the color of a pixel on the screen. And with fragment shaders, we can do all kinds of things. We can do the lighting calculations to make objects appear as though they're 3D. We can sample textures. We can do sorts of dynamic coloring and any sort of effect you've ever seen in a game where they've got like sort of energy rolling up them, or shields, or the sort of cloak from a Halo game, or anything like that. Very likely done with a fragment shader. We can also do create post-processing effects. We saw in the screenshots of Minecraft before that we can dramatically alter the look of the game simply by taking the render and piping that through a fragment shader to apply bloom and chromatic aberration, depth of field, all these effects that you see in all the big AAA games in your Assassin's Creed and Call of Duty and everything. But what else? What else can we do with fragment shaders? Can we store arbitrary data in a texture that we manipulate? Can we run particle simulations? Can we solve mazes? And you can look up shader solving maze after if you want, and there actually someone just did this recently. It's very cool. So the answer that I just kind of spoilered there, you can do basically anything. Oh my God. You can do anything in a fragment shader. The world is your oyster. So let's get into shader time and actually see some shaders in action. So here's a very, very exciting shader. This is our first fragment shader. I hope everybody just raise your expectations for what this is going to look like to the absolute roof, and then a little bit higher. So we've got another semantic here, boring DirectX stuff. It has to be there, that colon, SV's target, whatever. We've also got fixed 4. It's just like float 4, but it's only 8 bits per channel, which is perfect for colors because colors are 2 to the 8 is 256, and you can only have 256 values of red or whatever. Why did I write dreadfully uninteresting here? No, this is super exciting. It's got a 1 here. It's going to do something really, really hype. So let's check it out. If you can kind of guess what this is going to do, we're going to be returning a color, and we're going to return the color 1, 0, 0, 0. And if this is red, green, blue, alpha, and you could ignore alpha because we're not going to use it. You can guess. Oh, hey. Well. Yes, thank you. We've got one excited, and you're wearing red. Perfect. There you go. It's like I meant for that to happen. So let's go into our shader and have a little bit of fun. We're going to flip some bits. What's going to happen with this one? Dude in green. What's going to happen to it? He's on his phone. Okay, Mr. Green. This is for you. So something important did happen there, though. Something that I'll actually double back to, because we took our shader that all it was doing was returning flat red. It wasn't very interesting at all, but we were able to just go into it and change some of the values and see the effect it had, and that's actually will be a valuable way of experimenting in the future as you dive into shaders in your own studies. So let's do something. Let's actually cut the crap here and do something a little bit more interesting. So before we were just passing into our vertex shader, we were passing in this position, and we were just returning this SV position out. So let's make things a little bit more interesting by packing those values into a struct. And what that lets us do is it lets us specify other values we want to take in from the mesh and other values we want to return from the mesh. So in this case, we're taking in that texture coordinate, and we're going to return a texture coordinate as well for the fragment shader to use. So now our vertex shader, it's using that nice Unity object clip pause so that we don't have to think about all that math from before. And it's also just going to pass along that texture coordinate, or that UV coordinate. You can think of texture coord and UV as basically synonyms for one another. And now our fragment shader is going to do something a little bit different with the red and green channels. Rather than return a fixed value, a constant value of 1 or 0, they're going to return the texture coordinate we passed in. Texture coordinates typically range from 0 to 1. So along the x-axis of our square, we're going to go from 0 to 1. And along the y-axis of our square, we're going to go from 0 to 1. So what will that look like? Pretty, isn't it? Yay. So as you can see, as we increase in the x direction, the red value increases. As we increase in the green direction, the green value increases, and they all blend to yellow. If you're not familiar with how colors blend on a GPU, forget everything you learned from a color wheel about like, oh, red and blue mix and get purple. No, that's not actually really accurate. It's more like red and green mix and get yellow, and yeah. So actually, there's one more important thing to note here. So if you remember, our vertex shaders only run 4 times on this quad, right? And yet we have so many other values. So what's happening here is that the triangle that's generated on the GPU and the fragments it generates for us are actually going to interpolate those values across the surface of the mesh, if that makes any sense. So even though we only did 0, 0, 1, 0, or 1, 1, and 0, 1, or whatever, those values are going to actually be interpolated in a way that gives us smooth values to work with. So let's look at something in Unity. In Unity, we can expose these things called material properties, which let us pass in some stuff. So now that we're using a texture coordinate, let's expose a texture here. So you can all kinds of stuff: colors, textures, vectors, sliders, anything you can imagine that you might need to use in your shader. Primary way of just getting stuff into your material. So let's go ahead and assign a texture here to our shader. And I'll just quickly show the code for this. Again, this is sort of boilerplate stuff that you'll typically find yourself copying and pasting from other shaders you've written before, other people have written. I work in a professional game studio, and the amount of copy and pasting of old code, it's kind of atrocious. But it happens. So they follow a pretty fixed a fixed layout here of the shader variable name. This is how we'll actually refer to it in our code. They have this string value for the nice name we show in the other thing. That's why the color says fancy color or whatever it says. They've got a type, and they've got a default value. There's a few weird things in here, like Unity makes you have these curly braces because I don't know. And there's some extra parameters in range, for example. So our range slider can go from 0 to 1, so we actually have to specify that in there. So, all this out of the way, let's actually sample a texture. It's getting exciting. I got a good read. I can see you're excited. This is awesome. So we've got some new stuff here. We've got sampler 2D. That's basically saying this is a texture object, something that we're going to bind in our material properties so that we can use it in shader. And then we've got this function called text2D, which takes a sampler 2D as its first parameter, float2 as its second parameter, the float2 representing that texture coordinate, that UV from before, and it returns a fixed 4, which is the color of the pixel it's sampled at that position. So we had that that reddish, greenish, yellowish image before, kind of scaling across, sampling from 0 through to 1, and now we've assigned that picture of a cat. So when we text 2D, when we sample that, what will it look like? Meow. There you go. So I've been going a little quick here. I hope it hasn't been too much. Let's take a look at our shader so far. This is actually the full body of everything that would be in the Unity shader that generates that cat picture we saw a moment ago. So here's all the code we've actually seen and looked at. Here's those material properties we've looked at before. And there's a few other just generic Unity boilerplate things enforced by their syntax that have to be here, like here's the name of our shader, here's some other junk that we don't particularly care about. We have to say inside of our code here which functions mean which. So our function called vert is the vertex shader, and you can see it's there, vert. And then same with the fragment. Our fragment shader is frag, and here it is there. So before we start really hammering on some cool shaders, and actually we're gonna do a bunch of things to this cat. Wow, that was a terrible sentence. But we're gonna make it look a little bit more interesting. All right, so here's where we left off. Our cat. Sample the cat. Kind of cool, right? But we can do some other stuff. We exposed a color earlier, right? We had a fancy color on our material properties that we called underscore color. So how about after we sample our cat, we multiply by that color? So when we do that multiply, we'll say, okay, from the cat we sampled this red value, this green value, and this blue value. And if we specify color in our material, we'll say, okay, let's multiply by that red value by this one, the blue by this one, the green by this one. And that is the effect of sort of tinting our cat. And so you can see as we, in our material properties or whatever, as we drag that slider back and forth, we are, effectively tinting the image of the cat. So that's kind of cool. We can do some simple math with our colors. So we can do multiplications. What else can we do? Well, once we've sampled this value from the texture, it's just a number like anything else. There's nothing binding it to force it to be a color. So let's do something else. Let's just subtract it from an arbitrary value, from 1, the unit vector 1 here. So what we'd expect to see here is if we're taking 1 and we're subtracting our red value, and if our red value was 1, we'd get 0. If it was 0, we'd get 1. So everything is flipping, everything is inverting. Who here has opened up Microsoft Paint before and done like the invert image thing to a photo? Everybody's done that? Here you go. Boom, that's how you do that in shader code. That's how you invert an image. You take 1 and you subtract the color value you sampled from the image. That's pretty good, very Halloween themed. Thank you, cat. Let's look at another little fun function here called lerp. Very, very useful function that lets you mix colors and values together. And you can mix together things of different dimensions. So colors are sort of 4D values that you can mix, but you can also mix together positions. You can mix together texture coordinates, lots of stuff. It's an equation that's very fast because, again, shaders need to be run millions of times per second. So here's just the math behind it. You don't have to think about this too much because you can just write lerp and put in your color, your first color value, your second color value, and then that S value is a value between 0 and 1 for how much you want to interpolate between those two colors. So here's our shader from before with a little bit of modifications. You can see this time we're actually going to store the original color here. And then we're going to calculate the inverted color the same way as we did before, and we're going to hold a reference to that as well. And now our final color, the one that we're going to return, we're going to get by lerping from our original color to our inverted color using that slider, that 0 to 1 slider we just defined before in our code, in our material property block. And so we get this sort of effect where we can smoothly blend the photo of the cat between the inverted state and the fully colored state. So we can have one texture, why not have two? We can go back to our material property block and say, hey, we want a second texture. Let's just slot that in there, and Unity will automatically expose that for us on the material. We can assign a texture there, and we can use that in our shader as well. So I've assigned a little, you see I've got this, this sort of soapy bubbles texture assigned there with the cat. So we'll do our text 2D just like we did before to get the color of the cat. But now we'll also do another sample. We'll sample from our second texture, and we'll call that add color because we're going to add it to our main color. And we'll just add these together and return that. So we would expect to see these two textures here, the cat and the soapy bubbles, added together. And you can see there's a lot of black values in that bubble texture. And that's important because if we're going to add these colors together, anytime you add black, you don't change the value of that color, right? So we only want to change it where the soapy bubbles appear. That's cute. Look at that. Little soapy bubbles on our cat. That's nice. So bubbles tend to float up in real life, so let's try to do some animation on our shader. Let's see if we can get those bubbles to sort of slowly drift up in a way that kind of looks somewhat plausible. So you can do something like setting the game time, the total time that the app has been running, as a shader variable, and then use that in your shader for all kinds of stuff. You can use it to scroll texture coordinates, or you can use it as part of your lerp function, or maybe you pipe that into the sine, the trigonomic sine wave function, to get sort of an oscillating, repeating motion. Unity, luckily, has our back again, and it sets a value called _time for us, which has 4 sort of flavors of time. You've got 20th of time, you've got actual time, double and triple. You'll find yourself usually probably just using time.y to get the actual time, and then multiplying it to get to the period of time that you actually want. So now we're going to do basically the same thing, but rather than sample our bubbles texture with the texture coordinate we passed in, we're going to make a new texture coordinate in the shader here. So what we're going to do is we're going to take that unity time value, we're going to multiply it by 0.2, so that means every 5 seconds we would expect this value to go up by 1. And we're going to make a new UV for our use in the second sample here, which is going to be the x position's unchanged, so we're just going to pass that through, but the y position we're going to add to that y scrolling value. So what would we expect to see happen? It's going to scroll down, actually. So if you thought it was up, yeah. So if you remember, our texture coordinates look like this, and so if you can imagine the values at the bottom that are darker, that are closer to black and further from green, as they add and get closer towards green, they're actually sampling from higher up in the texture, which gives the visuals of it scrolling down. A little bit counterintuitive. Easy fix, though. We'll just flip the sign on the shader there, and with that, our bubbles scroll up. Nice. So let's just do that again. That was pretty cool. Let's just do literally the exact same thing, but we'll make a few adjustments. So we're gonna sample our bubbles texture twice here. Here's the first one. It's just basically unchanged from before, but I renamed some of the variables, and we're going to sample it again. This time we're going to use a UV that scrolls a bit slower. We're going to use a slower time scale, and we're going to offset the x value so that the bubbles never perfectly align. We don't want to get the illusion broken of having multiple layers of bubbles floating up to be broken. And then when we add all that together, we get this sort of this parallaxing effect of it. You kind of can't see as easily that it's just a scrolling texture because we've sort of layered on some things. And you could obviously layer on more and more. You'll effectively make your shader a little bit more expensive, but you can do this quite a few number of times without really hurting your GPU. So we've got a lot of code there for all this stuff. Luckily, though, like I said before, shaders are written in a C-like language, and just like C, we can make methods and function calls and stuff like that. So we can keep things a bit more organized by maybe taking our scrolling bubbles, all that logic we had before, and we'll just wrap that all in a nice function. So most of this should look pretty familiar in terms of function syntax. You've got your return type, you've got your parameters and all that. And then our code gets a lot cleaner. This produces the same shader, but we've put this in a function, and then this is up somewhere else in our code, right? The scrolling bubbles. So that's quite good. You can keep your code very organized. So we've seen so far we have a texture used that's just a cat texture, and then we've got another texture used that's sort of this additive, give us some bubbles to overlay on our texture. But just because textures, you tend to think of them as visual elements, but that doesn't mean they have to be displayed. You don't actually have to see a texture. We're just going to sample it for a piece of data that we can use in the shader. So any data or lookup table or whatever we want, we can just cram into a texture. So for example, we'll take a grayscale texture like this one here, which is all blacks in the center and sort of eases towards white towards the edges of the object. We'll call this a mask texture, and we'll call it mask text. And we'll have gone back to our properties before, our material properties, added a new material property with mask text, all that stuff. And then we'll take our exact same code as we had before, where we sample the cat, we sample our scrolling bubbles. But then, before we actually, or rather, while we're making our final color value, we won't just add the bubbles color as is. First, we'll multiply it by the value we sampled from the mask. And remember, that was a grayscale texture, so red, green, blue, those are all equal. So we can just grab the red component off of that. And so this will have the effect of masking out those bubbles in the area where the grayscale texture was black. Hopefully that makes some sense why that happens. You can kind of see here, if I go between the two, that that mask is defining the area of visibility for those bubbles. Yeah. So if textures can be textures and textures can be masks, what else can textures be? They can be effectively anything. Anything we can store and represent as, you know, an array, a 2D array of float 4s or 4D values, we can cram into a texture. Before, we saw that when we returned the UV coordinate, when we just returned it to see the colors, it produced something like this. So what if we did something a little bit weird here? What if we took those values that we saw returned by the UV coordinate and put that as a texture that we then assign into our shader? What would happen? So we'll assign that texture, and we'll try this out as an experiment. Assign that texture that looks like UVs, and then what we're going to do is we're going to sample the bottom texture here and use the value we get back from it, the red and green value, the X and Y value. We're going to use that to sample the cat. So let's go take a look at what that looks like. You can see we first set up our weird UV here, which is sampling our second texture. You can see I'm doing something here that's a little bit strange. I'm calling it XY. You can actually, all the values that you're getting back from a texture 2D call, you can refer to them as RGBA as the colors, or you can refer to them as XYZW, the 4D components. You can use those interchangeably based on the context usually. So we've got our weird UV that we sample from this texture. And then we're going to, rather than use the UV coordinate we passed in as a sample for our cat texture, we're going to use the weird UV. So what is that going to look like? It's actually not going to look very different at all, because that is the value that we saw when we went back and forth before with our UV coordinate. So that's interesting, because that kind of gives us a key into what other kind of weird things we can do. So there's no shader change at all here. All we've done is we've gone into Photoshop and taken that red and green and black, whatever weird texture, and just kind of mess up those color values. Put some filters on it, some ripples, all kinds of liquefy effects or whatever. And that's going to have a very interesting effect when we use this to sample the cat. We're going to make that cat not too happy. So rather than, that's a little bit too fixed, right? If we have to make a different texture in Photoshop every time we want to do one of these effects, we can't really use it a lot without having to bloat our project with hundreds and hundreds of new bespoke textures for every single distortion. So let's do something a little bit more creative then. What we'll do instead is inside of our distortion, or our second texture rather, we'll make this weird looking texture like this. And so you don't have to think about what this looks like visually. I mean, you can see it and it looks very strange visually, but all it is are values between 0 and 1 across the image. So what we're going to do here is we're going to multiply the UV coordinate by 4. What that does is it has the effect of tiling the texture 4 times. For those of you working in Unity, I'll point out that you have to have the wrap mode set to repeat. If you've ever seen wrap mode repeat versus wrap mode clamp in Unity, this relies on it being set to repeat. And what we're going to do with this, so this is a value that ranges from 0 to 1 everywhere we sample it, right? We're going to multiply that by 2, bringing us to a value between 0 and 2, and then we're going to subtract 1 from that. We've now got a value in the range -1 to 1. And that's something we could use to sort of distort our image, to distort our UVs. But we're going to use another helpful thing set for us by Unity here. This main text texel size, which you can see I have to define up here as well, is going to tell us how big is a pixel. So if our image is 512 by 512 pixels, this texel size is going to be 1 over 512 and 1 over 512. And then we'll multiply that by another slider that we put in our shader as well. So just something that gives us a value of basically, hey, how many pixels do we want to distort this thing by? All right. So once we take our texel size and our distortion magnitude into account, this value here, IUV plus distortion, that's what this might look like. So it's this sort of modulated, kind of slightly askew set of UVs. And now we have a distortion slider now that we can drag back and forth to change how much it's distorted, which looks like this. Whoa, dude. Sweet. So let's try something and put everything together we've seen so far. Shaders are built up of all these little, everything we've seen so far hasn't been particularly complicated on its own. It's like, okay, just multiply by this, subtract by this, sample this, whatever. But we can sort of build up all these different things into one sort of uber shader that compiles all these effects. We'll just do everything sequentially to sort of get a unique effect. For example, our UV distortion textures could also be masked or animated, so we could perhaps use an animated value for that distortion. Our distortions could be placed with the bubbles to make it look like the bubbles are actually refracting light if we had a distortion texture that looks just like our soapy bubbles texture. We could use our lerp to blend together distortion textures or other samples or whatever we want to do. Lots of different, very large possibility space here. So here are some of the textures we've seen so far. We have our cat, our mask, our UVs. We've got our bubbles. So let's do some fun things. We'll take our cat, and this is a Halloween-themed example, so prepare for spookiness. We'll invert the cat, because I thought that was spookier, right? I think that was pretty good. Our mask image is nice. It's got this kind of soft vignette feel, though. Kind of makes the cat feel a little like warm and cuddly. We want to obliterate that entirely. So we're going to make this terrifying-looking mask that masks out the cat's eyes, its whiskers, its nostrils, and sort of just a cloud of smoke around it. We'll use that for our mask texture. Our UVs, we'll of course do more UV distortions and rippling, because I thought the cat looked pretty cool while he was rippling and waving. And for the bubbles, let's just replace that with fire, because, you know, why not? Yeah. And so if you can imagine what the combination of all these things is together, it looks a little something like this. So yeah. So that sort of shows you in a really strange way what you can kind of do with all these things that we've seen so far. Like literally everything we've seen just compiled all into one uber effect of inverting the cat, adding the fire to the edges. We're masking out. You can see that the ears don't ripple as much as the fire because we're using our mask to ripple or to mask that out as well. And if this is too spooky for you, I understand. So here's a nice, happy, cuddly version of the cat. GIF compression is absolutely destroying this thing. But you can see we've used that effect I was talking about. So I now have a distortion texture for the bubbles that's perfectly lined up and scrolling with the additive soapy bubbles texture, such that you get this sort of, it looks like the light is sort of refracting as it goes over the cat. So these two effects, though, could actually effectively be made with the same shader, because they're all using the same things. They're just swapping out the texture, swapping out the distortion, swapping out the mask. You can actually achieve a lot of different things, which is quite cool. So wrapping up, shaders are an absolutely amazing tool. If this hasn't convinced you, then I don't know, go look up that maze thing on the internet, because that's pretty cool. And try writing your own shaders, or start by editing existing ones, because it can be a little bit daunting with all that boilerplate crap in there to actually start editing it, or to actually start writing your own. So maybe take a shader that you found online. I can actually speak with some of the TAs to see if I can get you guys the cat texture or the cat shader from today. And don't be afraid to break things. When you break something in a shader and you look at it in Unity, it will be magenta, and you've probably seen bright purple objects before in a project where something is breaking. You're usually looking at a shader error or a missing material, same thing. And you should be seeing that magenta. That means you're learning, so look at magenta for days like I do. Check out some other resources. I've got a couple of resources that I'm quite familiar with here. Alan Zucconi, very, very talented, very good resources, kind of ranging from beginner to intermediate shaders. Cat-like coding has a much more thorough, like I've taken a lot of content and really tried to condense it into this. Cat-like coding will break it out for you in a way that is much more approachable than 1 hour of somebody talking at you in a lecture hall. Game art tricks is more of just seeing what's possible with shaders. Simon does things like the wings from the angels in Diablo 3 and breaks down how that might have been done in shaders, which is a very cool resource. And so with that, I think we are done.